Okay, now I'm recording to this local, um, so I can put this a link to the video up on a link to the video. I'll put up on YouTube and put a link to it on Piazza. So graphs. Well, it's a set of nodes as vertices. These are objects of interest and a set of relationships. Well, the relationships are all of one kind, and they're also represented graphically as edges. So here's a picture of a graph. It's got four nodes, A, B, C, and D. And the edges connect the nodes. So here's a graph. Well, or it's a picture of a graph. It's a diagram of a graph. So we can say, well, it has four vertices. Like this might be four people, or it might be four other objects, or four stars, or anything. And the relationship could be is larger than, is a friend of, depending what the objects are. Okay, so when you draw a picture like this, you tend to call these vertices and these edges, and you still tend to call them edges when you refer to them as in a relation via a relationship, because this is just sort of a visual specification of a graph. Now, and so my set of nodes here is just the set of A, B, C, and D. But the question is, what is this set of relationships? Well, another way of specifying this, which then shows you how you can put this on a computer and do algorithms with it, because graphs actually figure quite largely in computer science. And if you want motivation, currently, if you go to a job interview, and this might change, of course, in a few years, but currently, if you go to a job interview, you get questions for programming. That is, you go to a technical job interview, and you end up having to do like a 30-minute programming problem, maybe on a computer, maybe on a whiteboard. And often what they ask you to do are simple algorithms. And currently, many companies ask you simple algorithms involving graphs, because this occurs at the end of a data structures course. So it is actually useful to know about graphs and how they're represented on a computer. Well, the first stage of that is to have, let's say this is graph G, then we can say that the graph G also equals a set where we represent each edge here as itself a set of nodes. Now, this is sort of symmetrical. If A is related to B, then B is related to A. So this is called an undirected graph. And in a moment, we'll get to directed graphs. Well, so here we have AB, we have AC, because these are sets, the order doesn't matter. AD, we need one more, BD. Okay, well, you could represent a set by this set form. And one thing to be able to do, one task to be able to do is to, I might give you this form, and well, I won't do that, but it's good to, because I can't really grade it or whatever. Or I might give you this form and then give you several of these and ask you which one of these is the visual form of the same graph or something like that. But the idea one is, or given this visual picture, what's the set form? Okay. So that's a simple graph, and this is an undirected graph. So what's a directed graph? Well, some relationships, for example, if these were people, and if the relationship was is say taller than. So if A and B are people or pieces of wood, well, I guess or buildings, say. If A is taller than B, then A is related to B, but B is not related to A. A and B, if there are people like A has met B, well, if A has met B, then B has met A. So that's symmetric. So undirected graphs have to do with symmetric relationships. Okay, so in this case, so let's say that this relationship, we might have a different form in which we might have a graph like this. So here's another graph, A, B, C, D. This is a directed graph. Directed meaning that because we put arrows, we sort of, the order matters, that A is related to B, but B is not related to A in the same way. So here we would write, we can still transform it as a set, but instead of using, like the thing is here for sets, AB equals BA, because in a set, the order doesn't matter. But here we're going to have a set of ordered pairs. Here we can say A, B, because the arrow is going to go from the first to the second, originates here, so that this corresponds to this edge. Then we could have A, D, and AC. We'd have to have DC, this one, and DB. So this is a directed graph specified as a set of ordered pairs. Okay, so that gives us sort of like the basic idea of a set. I mean, the basic idea of a graph, rather, and two ways of specifying, either as a visual diagram or as some kind of abstract set. Now, just as an aside, on a computer, matrices, which we haven't introduced, are often used to represent graphs. So that's something you can put on a computer. So what you do is you just to continue this is an aside. So for example, we might have the nodes label the columns and the rows. Then the matrix would be a two-dimensional array where if you put a 1 in here, that means that they're related. So these are not going to be, none of the vertices are related to each other. But for this directed graph up here, we can see that A is related to B, so we put a 1 there, but B is not related to A. So this is sort of like we go from here to here, related to this way. And then we'd have A is related to D, and A is related to C, but then these would be zeros down here because it doesn't go backwards. And then D would be related to C, right? D is related to C, but C is not related to D. And then D is related to B. And let's see, and C is not related to anyone. Let's see, oh, and D, whoa, D is related to B. Okay, that's this one there. Okay, so here is, and we've got, let me see, we've got 1, 2, 3, 4, 5. 1, 2, 3, 4. So you've got everything represented. So here's a matrix that represents this graph. And so it's not, it's like, it's a somewhat abstract sort of representation, but you could put it on a computer. And that's how you then do computer algorithms with graphs. One way, I think this is called, there's other ways of doing it, but this is what, there's many different ways of representing graphs on a computer, but this is, I mean, in terms of matrices or sets or lists or whatever. Sometimes you can just do it as a list with certain conventions. Okay, so that is, that's what's described here. What is a graph? I give some examples, how they're used, directed versus undirected graphs, set specifications, and then we come to our first concept, which is a path. So what is a path? A path is a sequence of nodes or vertices, if you want to call, if you're thinking of it visually. Nodes or vertices in which neighbors are directly connected. So let's draw another graph. Let's say okay. So let's say, so a path is going to be a sequence of these letters. So for example, AE is a path, but AEB is not a path because E and B are not connected, okay? So let me put one more line in here just to be that way. Okay, so then another path would be A, D, E, A, D, B, C. Because you go A, D, E, A, D, B, C. That's a path. B, C, E, D is a path. Just neighboring in the sequence, neighboring nodes have to be directly connected. So there's got to be a line, but an edge between the vertices and the graphical description of it. Okay. Now there's a special kind of path called a simple path. What is a simple path? Well, a simple path is a path with no well, let's look. See, it's paths versus simple paths. Okay, give some examples. A simple path has no repeated nodes with no repeated nodes. So, for example, this is simple. This is simple, but look, A and A, D and D, simple, simple, not simple, simple. Oh, here is A, B, C. It's a simple graph, and well, it's a graph. Then with three nodes, then A, B, C, A repeats the nodes. Also A, B, A. It sort of goes from A to B and back again. These are not simple. Okay, on a directed graph, a path has to follow the directions. So on this graph, we directed graph, you can actually list pretty much all the paths because all the paths are A, B. You can't have B, A because you have to, the path has to follow, A is connected to B. So that's one. B, D is a path. AC is a path. CD is a path, and AD is a path. Because there's 1, 2, 3, 4, 5, 1, 2. There's 5 length. These paths have length 1. Let's look at length 2 paths. Well, there's A, B, D, and A, C, D. And that's it. That's all the paths there are on this graph. In fact, all are simple paths. But you can't have directed graphs with non-simple forms. For example, we have this. So you can go A, B, C, A. There's a not simple. So it turns out, the way that they can be simple on a directed graph is by making a loop. Okay, so that's the idea of paths and simple paths. Now, a special case of non-simple paths are cycles. So what's a cycle? Well, a cycle is a path that starts and ends on the same node. So for example here, A, B, D, C, A, B, D, C, A is a cycle. It's not a simple path because it has a repeated node, but it is a cycle. Okay, so now we could also do, there's also ones A, D, C, A. And we can also do A, D, C, A, D, C, A, D, C. Just keep going around and around the loop. Okay. These are all cycles because the first node is the same as the last node. And the same idea works on undirected graphs. However, a cycle, so for example, on a this is a cycle, ABA, as well as A, B, A, B, A, or B, A, B, A, B, things like that. Well, there are paths and simple paths, and there's cycles and also simple cycles. So a simple cycle is a cycle um, that has no repeated nodes, but also no repeated edges. Okay, so for example, this is not simple because it doesn't, it repeats an edge, right? That's what, so we want, what we want to do is with capture with a simple cycle is one that goes around a loop only once. So for example, this one here, no repeated nodes except first last node. To be a cycle, it has to repeat the first last node. But you notice in here, in the middle, this one is not simple cycle. This is a cycle, but not a simple cycle. None of these, all the cycles in this graph are not simple. Now up here, ADCA, that's a simple cycle. This is not a simple cycle. ABDCA, this is a simple cycle. So a cycle goes around a loop once, but can't go around multiple times, and it can't go back and forth. So that's the idea of a simple cycle. So the tasks here are given a path, recognize, be able to count, like say on a directed graph, how many, whether a graph has a cycle or not, how, you know, whether it has a simple cycle. Some graphs will have um, cycles, but no simple cycles. For example, let's see if I can make one like this. Well, okay, so here's a graph A, B, C, D. I think if a directed graph has, if it has a cycle, this one has both simple and, for example, ADCA is a simple cycle, as well as like BCAB is a simple cycle, but it also has a non-simple cycle, which would be BCDECAB, which goes sort of like this. It goes in sort of the figure 8 one. So this is not uh, simple. It doesn't repeat in the edges, but it does repeat the node C. Okay, so that is the story on paths, simple paths, cycles versus simple cycles. Okay, so what you want to be able to do is sort of, you know, if I give you a graph and a series of nodes, is it a path? Is it a simple path? Is it a cycle? Is it a simple cycle? Any questions about this? Let me